Okay, for this week, in this module, we want to start with unstructured and then talk about semi-structured data and how they are handled in particular in relational databases. First topic I'm going to talk about are called large objects or LOBs, and then we'll spend most of our time talking about XML. So, first topic, unstructured data. So what does unstructured data mean? Well, think about it this way. When we're working in a relational database and we talk about our schema with different tables, right? So let's say I have a student relation, you've seen this before, and I have, let's say, an ID, name, a year in school, and let's say a GPA. All right, let's just say we have a simple schema like that. This ID may be a structured, right? It could be something like, well, we have a 10-digit number, right, at ASU that we use. All right, so I could specify that exactly. So for example, I could specify as a number 10, or I could do a fixed length character 10. The name could be a varying character, right? Varchar. Maybe we decide what some maximum or upper limit would be, like 128, something like that. Our year, maybe we go with a number for that, 1 through n. So this could be a small int or a tiny, or as it's called, or integer with a fixed length field, an integer 1. And then we can have a GPA, which is a real number or a float on here. And again, we could specify that down to the precision that we want. Now, why do we typically do such precision in relational databases? Well, one, relational databases are strongly typed. Our SQL language is strongly typed. And there's a physical underlying database reason for that. It's trying to optimize its physical storage, right? When I know how many, if I looked at a specific tuple or a row in a database of this kind, right? If I looked at this as, if I did this row by row, if I had 1, 2, 3, 4, up to 0 as 1, 0 up to 9 as the next student, James Smith, I know I'm scribbling here, Susie Q, year, James is a sophomore, Susie's a junior, James's GPA is 3.05, Susie's is 3.71. All right, when I map these things down onto physical disk on a server somewhere, I want to optimize their storage. I don't want the physical disk fragmented. I want to be able to optimize my underlying reads and writes to the file system in a scalable way. All right, so remember the origins of databases, right? We start off with record systems using tape, believe it or not, to mechanical drives, right? Now we do more advanced drives, but we were trying to optimize our storage so we can optimize our retrieval, and we didn't have to seek all over the place. We didn't have fragmented drives and the like. So there's an origin, or I should say an origin of the reasoning behind going from optimized storage up to strongly typed systems, right? But that's when we're dealing with a lot of textual data, a lot of record-oriented data, not the rich data types that we deal with now, and even unstructured data as we deal with. So the first time we started putting images and video and trying to manage those in our traditional relational database structure. Of course, there are ways that multimedia databases are built nowadays that aren't necessarily relationally based. But again, I'm talking about the transition to those kinds of data as we went to the internet age. All right, so dealing with unstructured data, that real world data is complex. Again, think of an image, an audio file, a video file, something like that. We don't have these fixed length textual oriented records that we want to store. That data is often unstructured, or at least carries with it its structure, meaning in the metadata, the header of the image, let's say, or the encoding of a video, what the structure of the data is. But again, we're used to in a relational database dealing with something that's strongly typed. We really kind of need something that's weak or typeless type, or really what we're looking for here is flexibility. All right, we need to be more flexible than this rigid structure up here that's trying to gear us toward fixed, or at least with an upper bound to maximize this kind of physical storage, if you will. So we need to be a little bit more flexible. Now, what if you're trying to do this as a programmer? So you're just writing an ordinary program, you could be writing it in, say, Java, right? If you're in Java and you don't know much about the type of data, you could simply treat all data as the root level object of the object-oriented hierarchy, right? You could cast it as an object type. and worry about determining its type at runtime later. If you're in a non-object-oriented language like, say, C, you can do a void star pointer, right? A typeless pointer that can point to just about anything you want in order to get around the typing constructs and things, okay? We want to treat data in its least restrictive form, all right? A stream of bytes. Unstructured means all we have are a stream of bytes. We don't have that metadata associated. We don't have the typing information associated with it. And what we want to provide in the database is a way to store that stream of bytes with little or no interpretation of what those bytes mean. So the way we do that, the way that evolved, I should say, in a relational database is use something called a large object, or LOBs. All right, and there's two types of large objects, so there is a little bit of specialization of the type. The most generic is this one on the right, the blob, binary large object. That's a stream of bytes. All right, that's all it is. A database doesn't really know anything about what is inside it. You have to carry your own metadata or have external metadata to know how to interpret that stream of bytes. Or you could have a character large object, or what's called a CLOB. Blobs and clobs allowed you to exceed standard physical sizes. So, for example, when you do a varchar of something, any database server that you install is going to have an upper limit on how large that varying character can be. You can't just say, hey, I think I'll go create a 50 gig size varying character field. Right? You can't do that. There's going to be an upper limit. A lot of databases now, you can create them quite large, 4 gig. I'm surprised, but back in my day, this might be as small as 4 megabytes. All right, but the point is there is an upper bound. Well, what if you have something larger than that you're trying to store? One is you'd have to use a large object. Typically, what a large object would do is kind of have a pointer. So this is an example using Postgres, which uses an OID, an object identifier, that would locate where the LOBs are stored. What that means is, as opposed to the fixed record object that I was just talking about a few minutes ago, all right, this thing over here for student that we were just talking about, right? Those rows are all stored in line because they have a meaning consecutively on physical storage is what I mean by the in line. Whereas here we typically would have some kind of external reference, and we would store the large objects separate, which means I'd have to read in a row with an OID and then go find where that OID is. It could be a separate spot kept on disk, meaning it would imply 2 different disk reads, which means it would take longer on top of the fact that you're probably reading across several pages of disk, given that it's a very large object. So one thing is just the physical size again, but the other part is, again, no type of metadata here. The only thing we know here is the C is a character. Tells us that it's textual. Otherwise, we could just treat it as a blob, a stream of binary data. All right. Now, when you deal with large objects, typically the solution you're going to do is going to be not portable. It's going to be proprietary based on that particular database vendor. So again, this is a Postgres example. It's not really important what Postgres specific. I'm just using it as an example. But notice how we declared these types of OIDs as the object identifiers, and then indicated files that I could go read into via an insert using these built-in functions. Right? LO import, that function is only defined for Postgres. You can't go over to MySQL and use large object import. That's what LO import is, and get the same thing. So again, there is a specific way of doing it per database vendor. There are some ways of dealing with it in JDBC. So we just talked about JDBC. There's a set get binary stream in the JDBC API. There's some new methods on connections and prepared statements and result sets that came out in the later version of JDBC. Again, there's vendor specific ways. We just talked about Postgres. So in Postgres, you can go into the jar file for your Postgres driver and find a type called large object. But again, that's going to be a database vendor extension. That's not part of the JDBC standard or SQL standard or anything like that. And that's typical of database vendors. Oracle does the same thing, right? They have a JDBC API standard way. It's a very clunky way of doing it. I can put out some sample code for you, but effectively, the code's quite clunky and frankly, can be difficult to ensure that you're closing resources correctly. Oracle has its own specific extension to JDBC involving their own type for a blob. Usually the vendor way is easier. They provide a set of convenience methods specific to their database platform and their drivers. So it's better supported, it's more robust code. It's actually one of the cases where I would suggest to you, if you were writing code using a large object, that you do so using the extension, which means you want to be very careful in your code to make sure you've factored that functionality off to the side, if you will, behind an interface, so you can keep your good object-oriented design and your principle of substitution. Okay, so that unstructured data and large objects, again, part of the evolution. As the nature of data became more rich, more multimedia, more data that would carry its own metadata. So this data that's semi-structured, maybe it's hybrid, it's part multimedia, part text, part different kinds of multimedia in it, for example. This WOB functionality and facility, became stressed. It really was going beyond its original intention, if you will. And it wasn't really expected to be used everywhere, right? I mean, it was always a design principle for the DBA and for the architect to basically try and avoid LOBs as much as possible, but use them when they were necessary, but you wouldn't see very many of them. And again, I've talked a bit here about the origins of LOB functionality being in physical layer optimization, not necessarily about the unstructured, semi-structured problem we're talking about here. There's a lot of research in this area. Again, a whole research area on multimedia databases, extensions to relational databases, object-oriented databases, XML databases that we'll talk about in a little bit. All came up as this, how do we evolve? How do we keep the things that we like about a relational database? Because there's a lot that we like, right? SQL is a universal language, well understood. Relational databases became quite mature, and there's value in that in the marketplace. But still deal with this new kinds of data. So the next wave became semi-structured, or some might say self-describing, meaning the metadata is contained in it. Nowadays you may use more than XML, but XML really became kind of the lingua franca, as they call it, the default language for self-describing and semi-structured data. So that's what we'll go forward and talk about next.